Okay, welcome back, everybody. So today is going to be a review class for the midterm, second midterm, which is on Thursday. So I've posted a few things on Brightspace in the past couple days. One is where this is an oceanography class, people might be interested in this. So tomorrow in this room at 1 p.m. There's an info, like a career event on meteorology. So that we have a couple of visitors, Mariette Hulen and Jordan Ford, who work for Environment Canada in the meteorology branch. And they are going to give a presentation on what kind of work does Environment Canada do in terms of meteorology and what kind of careers are available and that sort of thing. And it was a really good info session last year. So if you have any interest in that, feel free to stop by. I think it's going to be mostly career stuff, but there might be some just physics discussion of like what kind of stuff is involved. And that obviously pertains to ocean engineering and also physics. So if you're interested in that, either from the career or from the science perspective, it's open to everybody. So please feel free to join. The other thing is in terms of study materials. So I have already posted a quite detailed list of topics for the midterm. And what I'm going to do today is I'm essentially just going to go through that list and elaborate on each point, like write out the equations, what sort of stuff about those topics should you know, that sort of thing. And I've also posted the outline or the structure of the midterm, which is it's a 5-question test. The whole exam is only about, I think it's 4 or 5 pages long. 5 questions, and it's a mix of like sort of conceptual, like explain what something means or interpret an equation or something. Then there's a few questions that are related to using the equations that we talked about in class, so like maybe manipulating the momentum equation or linearized momentum equation, use one equation to drive another or something like that. But you will not be asked to reproduce from memory any of the derivations that I did in class. So for example, deriving the mass continuity equation, deriving the Wither equation. You won't be asked to reproduce those, but you might be asked to take it one step further given the starting point. There's going to be a formula sheet. So like for the first midterm, you shouldn't have to remember any formulas. And I think I should be able to post that formula sheet tonight, so you can have it in advance. The assignment solutions, my apologies, they have not been posted yet, but they should be up by about 7 or 8 o'clock tonight, so you should have them before it gets too late tonight, and all tomorrow. And if you do have any questions about anything on the assignments, either in advance of that or after you see them, please just let me know, and I can maybe make some time for some meetings tomorrow or answer email. Or even on Thursday. The exam's not until the afternoon. So if you had a question in the morning on Thursday, that would be fine too. Anything else? Oh yes. I was asked about notes, because of course I posted these very nice typeset notes early on, but I haven't managed to keep up with the notes of that quality. That's just been impossible because of time. And all of the material that's covered in the midterm, it's all in the online lecture. So if you just honestly, it's pretty quick to just go on YouTube and just click through until I refill all 3 boards and just see these are all the topics that were covered. You don't actually have to painstakingly watch it, or you can watch it on double speed or whatever. But if you do want written notes, today I posted some kind of pretty sloppy handwritten notes that I've been using to guide my teaching. So those notes do not cover things in the exact way we covered them in class, and actually there's some topics in those notes that we actually didn't cover. But if you want another resource, feel free to look at those also. But nothing will be coming directly from those notes. That's purely optional, just in case you want that, because there aren't typed up notes. Okay. Yeah. Well, one other thing I'll mention about I actually left this off on the description of the format of the midterm. There are a couple of questions, or one question of multiple parts, that deal with numbers. So you can imagine something like sound speed or something like that, right? So there's a couple of calculator type questions. So please remember to bring a calculator. I'll try to remember to bring a couple extras in case anybody forgets one, but it's much better to have your own calculator because you know what buttons do what and that sort of thing. Okay, so Yeah, so what I'm going to do is just basically go through the topic list and sort of expand on each of the points in that list. I will say, if you sort of just go through all those topics, you know, yes, I remember what we did, or I remember what that equation was, or whatever, that would be a great starting point for your preparation and the assignment problems. Although you can expect that some of the assignment problems were a little bit mathematically tricky with some guidance, like guiding you through the different parts. You probably wouldn't expect anything on the test to be as difficult as the sort of most complex assignment problems. Okay, does anyone have any questions about the midterm or anything that I've just said or anything about the course? Okay, all right. Well, in that case, let's just jump in. And I'm simply just going to go through the list of topics, and then this may take the full slot, or it may not. And if we have time at the end, we can do maybe a Q&A or something. Okay. Okay, so the first topic we really talked about after the first midterm, and again, just as a reminder, is that the second midterm is not going to cover explicit questions on anything that was on the first midterm. Some concepts that are sort of basic concepts, like maybe material derivative, are still involved, but you're not going to get specific questions on stuff that we did in the first midterm. So the first topic that we covered that wasn't really on the first midterm is the Euler momentum equation. And so this came from applying F equals ma to fluids, which we often call that momentum conservation. And the form of that equation was du dt equals minus 1 over rho, the gradient of p. And so here, d by dt is partial by partial t plus u dot grad. And the gradient operator is partial by partial x, partial by partial y, partial by partial z, and u is u v w. And so what this equation expresses is that the acceleration of the parcel, so in the first part of the course we saw that the material derivative of the velocity, that's the parcel acceleration, so how the parcel velocity moves, or sort of changes as that parcel moves. And so the acceleration is driven by this pressure gradient force, and then you divide by the density, which is sort of like writing A equals F over M. The reason this rho is in the denominator here is that the rho is playing the role of the mass. So you divide by the mass, multiply by the force, the pressure gradient, that gives the force. And so this is really, even though we write it as one equation, if we're dealing with 3 dimensions, u, v, w, this is really, it's a vector equation with 3 components. And in many cases, we look at simplified examples where we only consider, say, one of the components if it's one-dimensional, or maybe 2 of the components if it was the xy plane. But you can also understand the equation having full 3 vector components. That gives us 3 equations. So key thing is it comes from momentum conservation. Here's the equation. The interpretation is that the force divided by the mass is driving the acceleration. The acceleration is written in terms of the material derivative of the velocity. That's the Euler momentum equation. And we solved the Euler equation in simple cases. And so the main example that we did was we assumed constant density, rho equals rho naught, and we assumed that the pressure was given. And we used the example P of x is equal to A times x, where x is a constant. And so in very simple situations like this, you can actually solve the Euler equation. So a big concept that we talked about throughout the course is sort of equation counting and understanding when do we have a closed system. And so just looking at the Euler equation, this equation on its own is not closed because we have three equations, the three vector components for u, v, w, but there's 5 variables in this equation, u, v, w, and then rho and p. So you have 5 unknowns and only 3 equations. So this is not a closed system. But if you add extra information, you can make it closed. And one very simple trivial way to do that is just assume that the other stuff is given. So if you just assume that the density is a constant, you're given that constant, and that the pressure is just some known function. Here I've chosen the pressure to just be linearly, maybe plus p naught, linearly increasing with x. Then you can plug the pressure and the density into that equation, and then you're able to solve for the velocity field. And in this case, we reduced it to the equation du dt is equal to minus 1 over rho naught a, and this gave us u of t equals minus a over rho naught times t. And so any example that we did in the notes to solve one of our equations, one of our fluid dynamics equations, you should pay special attention to the examples that we did, because those are actually how we apply the equations. And so in this case, the key trick was we assumed that because the pressure, because the gradient of the pressure here is just a constant, it's just equal to basically A. Because the pressure gradient is uniform everywhere, we can assume that the flow along the x-axis is also the same everywhere. So we can write, rather than the partial time derivative, we can write du dt, the regular single variable derivative with respect to time. Okay, but this is very, it's a little bit unrealistic because in a normal situation, we're not given the pressure and the density is not constant, so we have to find those things together. So the next thing we did was introduce extra equations. So rather than say the density and the pressure are given, we said we had to augment the Euler equation with other equations. And so then we talked about the mass continuity equation. So our mass continuity equation. And this equation was d rho dt equals minus rho times what we call now the divergence of u. And this is kind of a similar point. We'll just do these together with the divergence operator. So the divergence operator is if we have some, so I'll just touch on the divergence, then we'll go back to mass continuity. So the divergence operator is if you have a vector field f of x, and so that would equal fx, fy, fz are the three components. Then the divergence of f is equal to dfx dx plus dfy dy plus dfz dz, and that's equal to d by dx, d by dy, d by dz dotted into fx, fy, fz. And so this is a standard operator in vector calculus. And so those of you that are taking the vector calculus course now have either seen this at this point or it will come up soon. And the key idea here is that you start with a vector. So when we take, say, the pressure gradient, so in the Euler momentum equation, the pressure is just a field. It's kind of like the temperature, right? There's one number at every point in space, that's the pressure. So that's a scalar field, and we take the gradient, it becomes a vector. So this whole thing is a vector. In the divergence case, we start off with a vector field with three components, and the divergence is now a dot product, which turns that original vector function we had into a scalar, which is just the sum of the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. On the assignments, you calculated this in some simple cases. Okay, so now this divergence operator, it shows up in the continuity equation as the divergence. This thing here is the divergence of the velocity vector. We sometimes write it as div of u, although not very often in this course. And so we could write this out in components as d rho dt plus u d rho dx plus v d rho dy plus w d rho dz equals minus rho times the divergence d. And this equation, this comes from mass conservation. And so we derive this equation by imagining how mass is flowing into and out of a fixed box. And the idea was that if there's more mass going into a certain box than is leaving, then the mass of that box has to be increasing, so that the density has to be increasing. And so this is an equation that tells us as a parcel moves, this is the material derivative density, as a parcel is moving around, how does the density of the water inside that parcel changing as the parcel moves? And what we found is that it's related to a minus sign times the density itself times the divergence of the velocity field. And so the fifth point on the list was interpreting mass continuity. And so here we had the idea that if you have there's really two cases. There's the case where the divergence is positive. And a positive divergence you can think of, just the word divergence. Things are diverging, they're spreading apart, everything is kind of expanding. And so a positive divergence would be a velocity field that's kind of spreading out like that. And what that's going to do is, if this parcel is a material parcel, that means it's embedded in the flow. That means the walls of the parcel move with the velocity of the flow. So if the velocity is spreading out, then it's going to pull the walls apart. I gave the example of if you had a balloon and you sort of put some glue on your fingers or something, you grab the outside of the balloon and then pulled it out, you would be expanding the size of the balloon, so the density of the air inside is going to drop. And so that's what we see here. In this case, we have d rho dt equals negative rho times the divergence. So the negative times the positive, so overall this would be negative, which says that when you have a positive divergence, your density is going to be decreasing because the parcel is expanding. So the density of the substance inside, whether it's an ideal gas or whether it's water or whatever, that density, so the density is going to decrease. Density decreases. And then our other case was the case of a flow with a negative divergence. So we call this a divergent flow. And the other case was when the divergence is negative, and we call that a converging flow. And that's just the opposite of this previous case. So we still have arrows, but now the arrows are kind of pointing in towards the center. So the parcel is kind of collapsing out of itself. The walls are shrinking in. And so in that case, we have d rho dt equals minus rho times our divergence. And so we get on the right hand side, we get a negative times a positive times a negative. So we get positive, so the density increases. And we did some examples of actually how to solve the continuity equation in particular cases. And so that was the next point on the list. So solving mass continuity in simple cases. And we did, I think we did a really simple example in class, and on the assignment you did a somewhat more complicated example that still had a nice exact solution. And so if we're given the velocity field, and initial density, mass continuity can be solved. To predict rho of x and t, or maybe in higher dimensions, rho of x, y, z, and t. And so we did the example of the straining flow, u was equal to lambda x, and we found that the density was equal to e to the negative lambda t. So this flow here, the divergence is just equal to lambda, which we assumed was positive. And so this flow was basically a flow along a line that looked like this. So it's getting faster and faster as you move along in x. And we just used a conceptual argument to say what that means is that our parcels are going to get more and more elongated as they flow down the pipe, because the right-hand side of the parcel is moving slightly faster than the left-hand side, because the flow gets stronger and stronger as you go down. So what that means is that that parcel is going to get stretched out, so it increases in volume, and so the density on the inside has to go down. Because the fundamental principle at the heart of this is that when we define a parcel of fluid, we mean that that parcel always has the same material inside it. So the same, we say this is our parcel, and then all of the molecules that are inside that parcel, they always stay inside it. So if the parcel volume expands, it's the same molecules inside, so the density had to go down. And so in certain simple cases, we can actually solve, if we're given the velocity field, we can solve for the density in the future. And so that's an example, and so there was an example on the homework and in class. And so paying attention to those couple examples is a good idea. Okay. But we went back to equation counting at this point, and we said, well, we have 3 equations from Euler, but we had 5 unknowns. And then so mass continuity adds 1 more equation. That's good. But we're still not done. We still have now 5 unknowns and 4 equations. So we still need another equation. And so our 7th topic here is thermodynamics, or energy equations. And now here is not something where you shouldn't feel like it's required to go and like look up a whole bunch of YouTube videos on thermodynamics or whatever. Just the very basics that we covered in class will be enough. So having some conceptual understanding of where the equations come from is really enough. And so we talked about a couple of ideas. We talked about the first law of thermodynamics, which is basically energy conservation. So usually it's written du equals dW plus dQ. And the idea here is that capital U is the internal energy of the fluid. So in this case, if it's an ideal gas, then that means that's really closely related to the temperature. It's linearly related to temperature. So this is the change in internal energy equals the work done on the fluid. So the fluid can either have work done on it, that tends to happen if you squeeze it down, or if the fluid expands, it does work on its environment, and that's negative work. And then dQ is the heating. And so that's like conduction. So like heat transfer is like if you touch a hot object, the heat is spontaneously transferred from that hot object to your hand, right? That's why you get a burn. And so, but you didn't do, the hot stove didn't do work on your hand, it transferred heat directly through thermal conduction. So dQ is the thermal conduction term. And generally we ignored that term. We actually ignored it in all cases because we were looking at sound waves. But it's just good to know in general in this equation what the terms means. We have internal energy, work, and then heat transfer. And then we said for sound waves, we said dQ was equal to 0, and we called that adiabatic. So adiabatic just basically means that the conduction of heat by molecular collisions is a fairly slow process. And for something like a sound wave, which is the first real phenomenon we studied, for something like a sound wave, the oscillations are happening so quickly, hundreds of times per second, that these slow processes of thermal conduction are just too weak and too slow to have much of an effect. And over a very long period of time, they can definitely have an effect. But over short periods of time, if you want to study a few sound wave oscillations, then you really don't have to worry about this dQ, and it's a very good approximation to set it to 0. And then our work term, dW, is equal to minus PdV. And so P is the pressure of the fluid, and dV is the change in volume. Again, you're not going to get a question where you have to like work on these formulas and derive stuff with them. Just having a general conceptual understanding of where the equations come from is what's important for this course. Just my notes really quick. We also had the equation, the internal energy is related to the temperature. So capital U is the internal energy. That's related to the heat capacity times or it's equal to the heat capacity times the temperature. And this is just saying that when we say the internal energy for an ideal gas, the internal energy really is just the kinetic energy of the individual molecules that are moving around the gas. And the kinetic energy of the molecules, that's the temperature. And so the internal energy is proportional to the temperature. The constant of proportionality that gets the units right, that's called the heat capacity. And then for ideal gases, there's a formula that says that the heat capacity is 5/2 times the gas constant. That's just a result from ideal gas physics. And at the end of this, I'll just write it on the side here, but we end up getting the formula P equals a constant times rho to the gamma, where gamma equals 7/5 equals 1.4. And this was really our last equation that closed our sound wave system. And this is called the adiabatic constraint. It's also sometimes called the isentropic equation of state. Isentropic, the entropic means entropy. And so isentropic basically means no change in entropy. That's associated with the fact that there's no heating happening. So when there's no heat transfer, there's no change in entropy. If you've encountered that topic in other courses, you're not going to have to use the word entropy on the midterm, so do not worry about that. Okay, but this last equation is very important because this now closes the system, because we have another equation that links pressure and density with this important factor of gamma is the adiabatic constant, that's equal to 1.4. And this is not an approximation, 7/5 is exactly 1.4. And if you take this equation, so we have one equation from here, we have one equation from mass continuity, and then we have three equations from Euler momentum. That's 3 + 1 + 1 is 5. We have 5 unknowns, U, V, W, P, and rho. And so now we have a closed system. So understanding that argument of how did we develop conceptually a closed system to describe fluid flow, that's important. And by the way, if anyone has any questions, feel free to pipe up, because I don't think I'm going to use the whole time, so there's time to discuss. Okay. Linearization. So linearization was a major topic. So 7, 8, linearization. So a key concept here in linearization is what does it mean, a linear equation versus a nonlinear equation? So linear versus nonlinear equations. And so in class, we talked about the example of a linear equation would be the heat equation. This usually has the form. It's often written in terms of temperature. So this is a partial differential equation that's appropriate for modeling, say, the temperature along a rod. So let's say you have a metal rod, looks like this, and you have T of x in time, so the temperature along the rod depends on your position, and also depends on time. And so modeling that, it turns out it obeys this equation here, called the heat equation. And the important thing is that we should be able to look at this equation and say, yep, that's a linear equation. It's linear because temperature only appears to the first power in both terms. There's no t squared, there's no sine of t, e to the t, none of that stuff is in there. It's just both terms are proportional to t. Another way to think about it is if you just took the temperature and doubled it, the 2 would cancel out. Like if you double t here and double t here, you cancel the 2's from both sides. That's linear. On the other hand, a nonlinear equation would be if we wrote something like dt dt equals k d squared t dx squared plus, let's say minus a constant times t to the 4th power. We use the example. And this is also a sensible physical model. This would be incorporating radiation. So if you were saying that this rod was cooling by radiating heat away, then you might add a term like this. But then this term is nonlinear, because that's the 4th power. So then this is the nonlinear term. And in general, linear equations are easy to solve. And when I say easy, what I really mean is that it's possible. So there's always going to be some technique you can look up in a book, or you could use computer software to solve it, or you might know how to solve it on your own. But either way, you can get the solution to this equation. And all linear equations are like that. On the other hand, nonlinear equations are usually impossible to solve. And so you can solve them on a computer. You can solve them numerically or approximately using something like Euler's method. But you're not going to be able to write down an elementary function like temperature equals the sine of time or something like that. And it's a general property of nonlinear equations that most of them are not solvable. Certain special cases are solvable, and we may discover solutions to more special cases in the future. But there's not any general approach for exactly solving nonlinear equations of this type. So that's the motivation of linearization, that we can do analysis very easily on linear equations, but not on nonlinear equations. So if we could find any way to take a nonlinear equation that we get somehow through physics and convert it into a linear one, that would be really good, because then we could solve it easily and do the analysis and understand all of the properties. So linearization converts nonlinear NL nonlinear into linear, and the assumption that's used. So you can't just do that for free. You have to make some sacrifice to get that advantage, to get that benefit. And the assumption that we have to make is that the fluctuations or the perturbations are small compared to the background state. And so as an example, we said, let's look at the pressure field in a sound wave. So P is the full pressure field, and we're going to write that as P naught, some background pressure, plus P prime. So this is the full pressure equals background pressure plus perturbation pressure. And graphically, we often thought if we look at sound waves in this room, then there's some background level of pressure that's about 1 atmosphere roughly. And then as anyone talks, if there's any kind of sound happening in the room, it means that you'll have your background pressure, but then the actual pressure will fluctuate a little bit around that background pressure. But the amplitude of those small fluctuations, the amount that the pressure is going up and down by, is small compared to the absolute pressure in the room. So as the pressure goes up and down, it doesn't get anywhere close to 0. It still stays like it's still always approximately 1 atmosphere, but just a little tiny bit more and a little tiny bit less. and that little tiny bit back and forth, positive or negative, that's the sound wave. And so because the little wiggles in the pressure are much smaller than the absolute background pressure level, that allows us to make a mathematical approximation called linearization that converts any nonlinear fluid mechanics equations that we derived using physical principles into linear equations that we can actually mathematically analyze with standard tools. Yeah, okay. Okay, so we linearized, so we applied linearization. So we linearized Euler, mass continuity, and adiabatic. And so it's a good idea to make sure you understand. So again, you won't be asked to reproduce exactly the derivation that we did in class. But it would be good to make sure that you can follow those derivations. And so we did this in one dimension. And so we assumed that P equals P naught plus P prime, rho equals rho naught plus rho prime, and U equals U naught plus U prime when we set U equals 0 in our calculations. But you don't have to. You could have U naught be not 0. We treated the 0 case. And so for Euler, we started off with du dt equals minus 1 over rho dp dx, which was really du dt plus u du dx equals minus 1 over rho dp dx. And this equation is nonlinear, so this is the starting point. This is before the linearization. And this one falls into the category of nonlinear equations for multiple reasons. This term is nonlinear because it's got u multiplied by u. I'll mention, when you're assessing linearity versus nonlinearity, you can almost pretend that the derivative symbols aren't even there. Derivatives themselves are linear. They don't cause nonlinearity. Capital D is different because capital D contains this term with u times d by dx. It's not the d by dx that makes this term nonlinear, it's the fact that there's u times u. So you can more or less ignore, just for the purpose of assessing nonlinearity, derivative symbols, things like that. Just look at, how many symbols are multiplied together. And then this term here is also nonlinear because it's just not a linear form. And so we linearized this, and we got partial u prime, partial t, equals minus 1 over rho naught dp prime dx. And so understanding where that came from is useful. And we had to use, I'll just write here as 9, some Taylor series. So this is the sort of an embedded topic. Taylor series for linearization. And so you can recall that for some function, f of x plus delta, that's roughly equal to x naught plus delta f of x naught plus delta times df dx evaluated x naught. So if you apply this, so we often have to apply Taylor series to do this linearization because we have to simplify, for example, this term 1 over rho becomes 1 over rho naught plus rho prime, and we wrote that equaled 1 over rho naught, I believe, minus rho naught 1 over rho naught squared rho prime. I think it was that. But either way, at the end of the day, we did a Taylor series to simplify this, but we ended up dropping this second term because this term with a rho prime was multiplying this pressure gradient, and that ended up being quadratic, so we dropped that term. So, but the key point with Taylor series is just that if you're trying to do a linearization problem, and you can't simply drop the terms because they're added, if there's like a division happening, or if a perturbation is inside a function, like if you had sine of the density, for example, then a Taylor series is often the way to simplify and be able to do linearization. And one that we used commonly, and if this is needed, this will be on the formula sheet, that the Taylor series for 1 plus x to the nth power is 1 plus nx plus dot dot dot. And so this is, you can actually prove this by using this formula, and this is often valuable in doing linearization. Okay, so we did the Euler equation, and then we did mass continuity. And so that started off as d rho dt equals minus rho divergence of u, which is in one dimension. We have d rho dt plus u d rho dx equals minus rho du dx. And again, this equation again is nonlinear for several reasons. This term and this term, they're both nonlinear, and that linearized to du prime dt equals minus rho naught du prime dx. And so just convincing yourself why these other terms ended up dropping out is important to know. And then we did adiabatic, which started off as P equals C rho to the gamma, and we linearized that as P prime equals CS squared rho prime, where CS squared equals P naught gamma over rho naught was our speed of sound. And so these three equations here, and these will all be on the formula sheet. You won't have to derive these or memorize them. All this will be on the formula sheet. But understanding what were the assumptions that we made to derive those, why did we do linearization, how we interpreted this speed of sound, those types of things which we went over in the notes. Those are the important things to know. About the speed of sound, so when we went through this linearization process, we just naturally found that in the adiabatic condition, we found that this combination of parameters, P naught times gamma divided by rho naught, showed up. And just as a reminder, P naught is the background pressure, that's about 1 atmosphere. Rho naught is the background density, that's about 1.2 kilograms per meter cubed. And gamma is just that 1.4, just a pure number. So this just popped naturally out of our analysis. And what we showed was we looked at the units of this, or the dimensions. And what we found was that the dimensions of gamma P naught over rho naught were equal to length squared per time squared, or length over time squared, which is velocity squared. So whenever you get a combination of parameters that show up in your analysis, that they're all kind of grouped together, they're all multiplied together in this particular ratio, usually a very useful way to try to interpret the meaning of that is just to find out what the units are. And in this case, they're the units of velocity squared. And then the next class, we actually showed that this CS is actually the speed that the sound waves travel at. If you plug in the numbers, you get CS is 343 meters per second, plus or minus a little bit. Okay. Oh, and so something that this equation shows us is that as the pressure and the density change, which are also linked through temperature, you can also write this in terms of temperature, it's a very nice way of doing it too, that the speed of sound is going to change. So the speed of sound is not universal in air, and it's also not universal in water. It depends on the properties. In particular, it actually depends on the temperature. We didn't really go into that, but it depends on the background pressure and the background density, sort of more fundamentally. Okay. All right. So after going through linearization, we talked about the wave equation. So when we linearized Euler, mass continuity, and adiabatic, we got three equations that are now linear, but it's still three coupled linear equations, partial difference equations. But then we talk about how they can be combined into the wave equation. So 10 is the wave equation. So we showed that Euler, adiabatic, and mass can be combined to give the wave equation. And the wave equation was that we wrote it in terms of the pressure. So the second time derivative of the perturbation pressure is equal to the sound speed squared times the second x derivative. And this equation is called the wave equation, very general equation. And it doesn't just apply to sound waves. It applies to all other or many other types of wave phenomena, including waves in musical instruments, like waves on a guitar string or a piano, waves on the surface of a drum head, waves in the atmosphere, gravitational waves, all sorts of different things. Underneath the majority of wave phenomena, there's some equation that looks like this. And we have a particularly simple case where the sound speed is just a constant number. In many cases, the sound speed might depend on space, for example. So you might have, or the wave speed might depend on space. And that actually happens in surface gravity waves, which we're going to talk about towards the end of the course. This equation, we talked about how it has traveling wave solutions. So we said, let's look at solutions like P of x and t equals a constant times sine of kx minus omega t. So this is called an ansatz, A-N-S-A-T-Z. And an ansatz is just a guess where you plug in a trial form. You plug in a formula that you think might be a solution. And very often, that trial form has some free constants in it. So right now, our P prime formula has three constants, the P, capital P, little k, and little omega. And those have all a name and a physical interpretation. So capital P, that's called the amplitude. Little k is called the wave number. And little omega is called the angular frequency. And then amplitude is, we talked before about how in a wave, the pressure is just going up and down a little bit. And so the amount that goes up and down, actually half the amount, is your P. That's your amplitude. So how high the pressure goes relative to the baseline, that's the amplitude, and how low it goes, that's minus the amplitude. Then the wave number, k, is related to the wavelength of the wave is 2 pi divided by k. So there's a standard conversion between wave number and wavelength. And then we often also talk about waves in terms of period rather than angular frequency. So the period of a wave is equal to 2 pi divided by that angular frequency. So you could very easily rewrite this same traveling wave ansatz. You can write it in terms of amplitude, wave number, and angular frequency, or you can equally correctly write it as amplitude, wavelength, and period. But basically, to avoid fractions, physicists normally write it in terms of k and omega. It just makes there's less factors of pi all throughout your equations, but it's the same physical movement. And so this is our ansatz. And then there's a question, I mean, this is basically just a guess. And so does that guess actually solve the wave equation? Do sound waves actually look like this? Sound waves look like whatever solves this equation. If we can solve this equation, that's a sound wave. But does this satisfy? So to check that, what we did was we took our ansatz and we plugged it in to the wave equation. And we found this formula that we called the dispersion relation. So point 11 was the dispersion relation. And so we plugged our ansatz into wave equation, and we derived the formula omega squared equals CS squared K squared. And this formula is called the dispersion relation. And I remember when I first encountered this was actually, you guys are seeing this in second or third or fourth year, depending on where each student is. Well, I actually didn't really see this concept and understand it until I was a graduate student. And I found it confusing when I first encountered it. Like, what is the meaning of the significance of this equation? But what it really tells you is that in sound waves, the frequency and the wave number of sound waves cannot be arbitrary relative to one another. So, for example, if I tell you, let's just suppose we have CS is 343, and let's say we have a wave with period of 1 second, for example. That'd be a very low frequency sound wave. But then we would then say that the angular frequency is 2 pi divided by 1 second equals 2 pi seconds inverse. And so that tells us right away that K is equal to or K squared is omega squared over CS squared is 2 pi per second squared divided by 343 meters per second squared equals some number. So the point is, you can do, I'm not going to do the numerical calculation, but the point is, if I just tell you just the, you know the sound speed, which you could compute from pressure and background density, those would be given. And if I tell you what the wave period is, then you can compute the angular frequency from that, and then from the dispersion relation, you can tell me, without me telling you anything about the spatial structure of the wave, you can tell me the wave number, and then from the wave number, you can tell me the wavelength is 2 pi over k. So there's a very rigid one-to-one relationship between the temporal properties of the wave, the angular frequency of the period, and the spatial properties of the wave number or the wavelength. And you can't have sound waves which are arbitrary mixes and matches of any two period and wavelength. They go together. So for each period, there's a specific wavelength. For each wavelength, there's a specific period. And they're linked together by the sound speed. And so that's what the dispersion relation says. It says that our solution, our traveling wave ansatz, is a good solution. It is what sound waves look like, but not for any k omega, only for k omega pairs that obey the dispersion relation. And so it puts a very significant restriction on what types of behavior the waves can exhibit. They can't be arbitrarily fluctuating in space and time. The time fluctuations and the space fluctuations are rigidly related. Okay. Okay. So then we talked about the concept of wave speed. So 12. Wave speed. So our traveling wave, this is x, at a particular point in time might look like this, where this would be, if this is pressure of x and t, you might have a p prime. So you might have a high pressure here and a low pressure here. But then a little while later, if this wave's a traveling wave, it might look like this. And so basically each point on the wave has advanced. The whole wave pattern has shifted to the right, and each little bit has shifted by the same amount. And there's a certain delta x by which this wave pattern has moved. And if we took delta x divided by the elapsed time delta t, we would call that c, which is the wave phase speed. And it's called the phase speed because actually there are three different notions, at least, of speed when it comes to waves. There's the motion of the pattern. So this is what people normally think of the speed of the wave. And so this is this delta x over delta t. The whole pattern is shifting downstream at a certain speed. And this is the same kind of speed that you would observe. It's kind of a dumb example. I remember I used to think this example was kind of stupid, but it's actually not. It's a good example of the wave in a stadium. So if you're at the stadium and you see people doing this, and it goes all around, that pattern travels, and you can watch it travel across the arena. But each individual person is not actually running with that pattern, right? We all know we're staying in our seat, maybe getting up and down a little bit, but then the pattern moves at a certain speed. How fast does that pattern move? Well, you could measure it, and then you might ask, what controls that? Well, in terms of the wave in the stadium, it has something to do with human perception and psychology and reaction speed. Like you see it coming, you get ready, and then you go, and so something's going on in your brain that tells you when to get up and sit down. And so there's some kind of physics or physiology or human psychology that determines the speed of the wave. But in either case, what we call that wave speed is the speed at which the pattern moves. But that's totally distinct from the speed at which the people inside the wave are moving. So the fact that you so first of all, you're not even moving in the same direction, because the wave's going around and around, and you're just standing up and sitting down. So you're moving up and down, the wave is going this way. So that same thing is true for other kinds of waves, that there's different notions of velocity. So the wave phase speed is like the speed of the wave going around the stadium, and that's the speed of this pattern propagating downstream. There's also the notion of the motion of parcels of air or parcels of fluid as part of the wave. So in a sound wave, the parcels of air are gyrating back and forth a little bit as the pressure wave goes by. And that's a totally different speed than the speed of the propagation of the pattern. Those two things do not have to be the same, and they're not the same. And then so there's particle speed. So there's three notions of speed. We really only talked about two of them. So there's phase speed. That's the speed of the pattern. Then there's particle speed. And this would be the actual u prime of x and t field associated with the wave. And so that would be, in this case, the speed at which you're literally standing up and sitting down in your seat would be the particle speed. That's the speed that the individual element is moving, which is distinct from the speed of the pattern. And then the third notion is called group velocity. And we have not covered this yet. So I'll just mention that it's a third notion of speed. We might cover this towards the end of the course. And the group velocity, I'll just comment, this will not be on the test, is the rate at which energy travels. So waves can carry energy. We know that, for example, because the electromagnetic waves that we get from the sun, we can run, photovoltaic stuff off of it. So those waves carry energy. We can turn that energy into electricity or whatever. And so the rate at which energy propagates is actually a third type of velocity. But the key thing is the phase speed. That's the one we talk about the most. And so the phase speed we showed formula that the phase speed is equal to the ratio of the angular frequency to the wave number. C equals omega over k. And we showed that for sound waves, the dispersion relation tells us that omega squared equals c squared, cs squared, k squared. So omega over k squared equals cs squared. So c equals plus or minus cs. So the wave phase speed equals the speed of sound. And so this was the actual proof, or the demonstration, that when we write down this traveling wave ansatz, we can ask, for a given k and a given omega, how fast does this pattern propagate downstream? And then we looked at this notion of an observer that runs along with the wave, and we said that that observer has to run at the speed omega over k to keep up with the wave. So that's the speed of the pattern propagation. And then for sound waves, it turns out that this ratio, omega over k, is always equal to cs, the speed of sound. So this thing that we call the speed of sound, it actually is the speed of the waves. And so that 343 number is the rate at which any sound wave is going to travel at this particular pressure and density that we're at the Earth's surface, P naught and rho naught. Okay. And then the last topic that we covered was dispersive versus non-dispersive waves. So 13, dispersive versus non-dispersive waves. And so we showed that all sound waves, whatever their values of k and omega, all travel at the same speed. C equals cs equals 343 meters per second. And so from our calculation, this might seem obvious. This kind of just happened naturally. This is the wave speed. But actually, sound waves are a particularly simple kind of wave in that all waves of different sizes, meaning wavelengths, travel at the same speed. So in particular, different wavelengths or frequencies travel at the same speed. This is called non-dispersive. So waves are called non-dispersive when they have this property that they all travel at the same speed. Light is also like this. So if you study electromagnetic waves, light waves are also non-dispersive. But we'll see in the last part of the course that actually surface ocean waves are not like this. Surface ocean waves are different. They're called dispersive. And that means that different wavelengths travel at different speeds. So non-dispersive is different wavelengths travel at the same speed. Dispersive waves travel at speeds that depend on wavelength. So often, longer wavelength means faster propagation. we didn't talk about this particular point, so that's not going to be tested. But the notion of what's the difference between a non-dispersive wave, which is like a sound wave, everything travels at the same speed, and dispersive waves would be waves where all the different waves all travel at the same speed. So if you have a sound wave, if you have a wave with a wavelength of 1 meter versus a wave with a wavelength of 2 meters, those will actually propagate at different rates. And it's very easy to imagine that dispersiveness versus non-dispersiveness is very, very important in practice because, so if we imagine, let's suppose the sound waves were dispersive, so that different wavelengths traveled at different frequencies. What that would mean is that if I was playing a piano piece up at the front here, and I hit 2 keys at the same time, a high C and a low C, then those 2 sound waves would actually reach your ears not at the same time. There would be a gap between them. So you would hear one first and then the other. And so imagining how you would make music or how you would speak or how you would transmit information with sound waves, if they all travel at different speeds, you would need like computer data analysis to figure it all out. You couldn't just hear it with your ear, but it would make sense. And so dispersive waves and non-dispersive waves behave very differently in practice, and sound waves are the simple kind, and that's why music makes sense and human speech makes sense. And if you try to do something analogous with ocean surface waves, you run into all kinds of problems because your low frequencies would travel faster than your high frequencies. Okay. And so really for that, it's just really just the concept is the important thing. Okay, so it turns out I did use most of the time, so we only have about 5 minutes left. But that's really all the topics. Let me just double check. Let's see, did we cover everything here? Oh, I should mention the ideal gas law. When we were talking about ideal gases, I didn't actually write the ideal gas law on the board, but that'll be on the formula sheet if necessary. You might be asked, for example, like you know a pressure and a density, calculate a temperature. So you'll have the ideal gas law for that. And that's about it. So, so as I said, I'll post some stuff this evening before it gets too late. All the assignments will be posted. And if anybody has any questions, you can feel free to send me an email or try to schedule a meeting. Or if anybody has any questions just based on this in the last 5 minutes, I'm happy to take questions also. But other than that, I would just end it there. But does anyone have any questions? Yes?
So the volume 2 of the course notes, are you going to post that too?
No. So sorry. I think maybe you might have been. Did you walk in just a couple minutes late or something? So what I said at the beginning was the course notes, the typed up course notes, unfortunately, I don't have time to make them as nice as before. So what I did do was I posted some handwritten notes. And those notes are not nearly as good as the typed up notes, but they do cover a lot of the same material. My warning with those is that if you want, so the purest form of lecture notes is on YouTube. So if you go on the internet, on YouTube, all of the notes are on there. But if you want something written out, then you can use the post-it notes. But they don't follow along exactly the same way I did it on the board, because I think I improved it a little bit this year relative to last year. But if you do have any questions, definitely you can let me know, and I'm happy to answer any questions that you have. But what I would recommend is if you really want to get, the midterm will not be, nothing from those notes that is different from what we covered in class will be covered. So it's just what was covered in class, that's everything you need to know. And so I might recommend going on YouTube and watching it at double speed, or just clicking through. Each time I fill up a board, just click ahead and don't listen to what I'm saying, just look at the board maybe. Because I know it takes a long time, I understand that. But unfortunately, producing those typeset notes is a lot of effort. And I'm hoping to get them done for next year, but they're not going to be done by I wasn't meaning to accuse you of being late or anything. I just made some comments. It's okay to be late. It doesn't matter. Yeah. Any other questions? Okay. All right. Well, I'll end it there. Please just let me know if you have any questions or anything like that. Try to remember to bring a calculator. And other than that, good luck with the rest of your preparation. You should expect something of a similar level to the first midterm. The first midterm was fairly well done, so I'm sure this won't be, will be good also. Okay, I'll see everybody on Thursday, and I'll keep an eye on my email and look on Brightspace tonight because we're going to post some new stuff. Okay, thank you.
Thank you.
I didn't mean to jump on you for being like, yeah, sorry. That just came out of my mouth. I was like, oh, shit.
I'll do some of the
Yeah.
ones, bro.
I'm really